Okay. Uh, right. So, so let's just briefly recap. So, as I said, the whole point about logic and computer science is that we are somehow interested in mechanization, especially of logic, because it is sort of fundamental and can be used for checking, getting clarity about the nature of proofs in mathematics and all mathematic allied subjects. And of course, within computer science, logic has a large role to play. I mean, it has applications to program and system specification and verification. Logic is also used as a declarative programming language. Many of you must have studied Prolog in programming languages. It's there. Equational logic is widely used in constraint programming, and of course, in this there is this hot and important area of theorem proving within areas of mathematics and outside. Yeah. Okay. So let's start with formal logic. Right. So we'll start. Everybody, of course, knows propositional logic, but it is necessary for us to establish notation and notation and conventions and so on and so forth. So what I'll do is I will briefly go through propositional logic, and then we will start with. We will spend a lot more time on first order logic and some other logics. But propositional logic forms the basis for all other logics. So therefore, it is important to sort of look at it. So it's important to establish notation, especially because I have peculiar beliefs on notation. Yeah, that's one reason. Probably the most important reason, and therefore much of my notation may not be found in normal textbooks. Yeah. Okay. So, but however, we live with my notation because it's obviously better than all other notation. So, okay. So, and also we need, what I will do is, I will take a distinctly algebraic view of the whole subject. In fact, logic is essentially an algebraization of reasoning. And no book actually tells you that, but it is implied. And therefore, I will take a distinctly algebraic viewpoint. Right? The whole idea of algebraization, as it was inspired essentially through Euclidean geometry, was that it was much harder to deal with the nature of proofs and their correctness within a geometrical reasoning system. However, if you algebraize it, somehow things become easier to at least verify whether certain proofs are correct, firstly. Secondly, algebraization means also, though it was never specified by anybody, even logicians, algebraization also means using a formal language. And programming languages, for example, and all formal languages are actually inherently algebraic in nature. Right? So, there are two primary viewpoints in mathematics. One is algebra and the other is geometry. And a large part of the effort of formalization of mathematics, and these two forms have actually kept on. So you can think of it this way. When coordinate geometry came, that was essentially an algebraization of Euclidean geometry. So you could, I mean, so the notions like lines and points and so on could essentially be specified as some equations, right? So as algebraic equations. So the relationship between algebra and geometry has always been, I mean, they have looked different. The nature of proofs was different, but they have always interacted with each other. So the notion, but logic is algebraic in that sense. There is a formal language which basically, since by now all of you know that all programming languages are essentially some kinds of term algebras, right? Right? All formal languages are some kinds of algebras. You can think of any programming language as essentially a set of basic constructs with some operators. The programming language constructs are essentially the operators. So the moment, and then you can think about equational reasoning, you can think about specifying things as identity. Equations is a general term for also identities. It's not just for solving equations. Okay. On the other hand, the concept of recursion in programming languages itself is actually the concept of solving an equation in an unknown, namely that name that is being specified recursively, right? So there is, any formal language is actually algebraic in nature. What logic gives you from geometry is really the notion of axiomatization. Is essentially inspired by Euclid's elements. Essentially the idea that there are a few basic axioms or postulates and everything else should be derived as a theorem from these basic postulates and axioms. So that is the interaction between algebra and geometry, and since we are essentially dealing with it as a formalized system, we will look at it algebraically, mostly algebraically. Yeah. Okay. To set the stage for the algebra, the first thing, of course, as I said yesterday, was that we'll talk about truth and falsehood. Truth and falsehood, as far as we are concerned, the underlying model of truth and falsehood is just two values, right, belonging to a set 0 and 1, and I'm using brown color because it's very down to earth. So 0 and 1 are the Boolean set. You can regard it as being embedded within the natural numbers, or you can regard it as being separate from the natural numbers. Okay, but either way, it's essentially our semantics will all be specified in terms of this Boolean algebra. And this Boolean algebra, I have also defined it in some peculiar fashion. Well, there is this inverse operation, and there is this product operation, and there is this summation operation. And then there are these two relations, less than or equal to and equal to. Okay, so any algebraic system, as you know, consists of a carrier set, a collection of operations, and a collection of relations. And that's what our Boolean algebra is for, right? And Boolean algebra, of course, is specified as a set of equations, if you like, as a set of identities, right? Okay, and remember that we are doing mathematical logic in which we are using the tools of mathematics itself to specify logic also, to deal with the notions of reasoning in logic, right? So we have the two element Boolean algebra, where the operations take their usual meanings, yeah? So you can regard this dot either as a product operation or as a minimum operation, minimum of two numbers taken from this set. This plus, of course, is Boolean summation and not addition. Yeah, so they are operators within that Boolean algebra. Right. So we'll just take for granted this algebraic system and all its properties. Yeah, and this algebraic system and all its properties are going to form the basis of the notions of truth and falsehood on which the language of logic is going to be built. Yeah, so the language of logic is, and the meanings, there is syntax and there is semantics, right? So for every syntax you have to give a semantics. The meanings will be expressed in terms of this notion of truth and falsehood. I mean, this is the most concise way I could think of representing truth and falsehood, right? Right. So now, so you all studied these Boolean algebras and their properties and various things. So for example, you could think of, I mean, there is there is also another kind of duality which goes on, and that is that of model construction. And in a certain way, the hardware circuits that you have studied about are really like models of this Boolean algebra. But when you study hardware circuits as models of this Boolean algebra, then you are looking at this Boolean algebra itself as a language. The expressions of this Boolean algebra as a language, whose meanings are given through the workings of those circuits, AND gates, OR gates, whatever, NOT gates, and so on and so forth. On the other hand, what we are going to do is we are going to take this algebra itself as well understood, and we are going to build a language whose meanings we are going to express in terms of this algebra. So the question of, so in mathematical logic, therefore, depending on the viewpoint, certain things can be models or they can be the object of study. Yeah. So these operators, I'm going to define them in terms of the natural numbers. As far, if I think of them as essentially a subset of the naturals, I have to just ensure, however, in any algebraic system, I have to ensure that the operators are closed on the carriers, right? You should not have to go outside the carrier set. So even so these operators, I'll just think of them as this. This is the most, it's a convenient way to think of them. So this minus that you see is not really part of the Boolean algebra, but it's actually part of the natural numbers, the subtraction operation in the natural numbers. Yeah. Max and min are also operations on natural numbers, if you like. Okay, and then of course the notions of less than or equal to and equal to on Boolean algebra are well understood. Though equality is actually a very subtle object, subtle relation, and we will have the need to define various kinds of equality. So, for example, even in the case of programming languages, when you actually copy a program straight off, let's say from one file A to another file B, A and B are equal in certain senses. A and B are equal in the sense that they are both syntactically identical. Okay, that is a kind of equality that A and B are. A and B are also equal because since they are identical copies, the meanings of the two programs are also the same. So they are equal as programs. They are equal in terms of their program behavior. They are syntactically identical, they are also equal in their program behavior. However, the two files A and B are not the same file. Okay, so in terms of, are A and B the same object? They are not. They are different, they are still different objects, and therefore they are not equal in terms of their identity. A simple distinguishing feature of A and B is that they would have different inodes in the operating system. Right? So they are not identically the same element. So equality has very subtle meanings depending on how you look at it. So there is identity of elements. There is syntactic identity, but between different elements. There is the equality that comes just from the fact that I am calling the same object by two different names. Okay? So there is, so copy is one thing, soft link is another kind of equality, a hard link is a third kind of equality, and they all have subtle differences. Right? I mean, most of you have also done a course on operating systems, right? And you already you use soft links and hard links and so on. So you can see that each of them actually has a different. So aliases. So two names may be aliases for the same object. Okay, in which case that's an equality that goes even higher than syntactic identity. They are not only syntactically identical, they are also the same object, right? So at some point, these subtle differences between the various kinds of equality will also become important. Okay. Unfortunately, in mathematics, equality is not greatly distinguished for all its subtle variations. So when we look at this Boolean algebra as a model, we are looking at that equality within this Boolean algebra. Whatever the Boolean algebra says are identical, they are identical, and that's why I have this brown equal. So my color coding is also going to sort of distinguish these subtle differences. So this equality is a mathematical equality defined on this Boolean algebra, right? Okay, so I hope the colors are clearly visible. No? Okay, right. So now, does anybody have problems with the colors? Okay. So now you have these two less than or you have this equality on the Boolean algebra, and you have a less than or equal to, where this less than or equal to actually comes from the natural numbers. So 0 is less than or equal to 1, and 1 is less than or equal to 1, and 0 is less than or equal to 0. That's, for this set, that's all there is to it. Yeah. However, the Boolean algebra is also a peculiar thing, because I am using it as a representation of truth and falsehood. It is possible to consider these relations less than or equal to and equal to. It's possible to look upon them also as operators. And I don't mean as operators in the same sense in which any relation in a program is regarded as a Boolean function. I don't mean it in the same sense. It's because it's Boolean that this relation as a Boolean is also an operation. And so I'll use a dot in front of these relations to regard them as operations. Okay, this is the problem. This is one problem with me, in the sense that these are not things that most books would specify. Yeah? Okay, whereas so what I'm trying to say now is that with this less than or equal to dot and equal to dot, I have essentially an algebraic system in which there are 5 operators instead of 3. Instead of 3 operators and 2 relations, I can think of them as 5 operators whenever I want to. But that's a convenience that that's a flexibility between that I will exercise whenever I need, right? Okay, so this is the interesting thing. So A is less than or equal to dot B, where less than or equal to dot is regarded as a binary operation, and it's equal to 1 if A is actually less than or equal to B, and 0 if otherwise. Yeah. And similarly, A equal to dot B is 1 if A is equal to B in the Boolean algebra. Otherwise, it is. So that's like, actually, it's since they are there are notions of truth and falsehood with 0 representing false and 1 representing true. We can also look at the truth and falsehood of these relations themselves within the Boolean algebra as operators. Yeah. Okay. So we will start with propositional logic and establish essentially our notation. So we start with a set A, which is a countably infinite collection of propositional atoms. If you like, is another word for it. So we are essentially defining a language, and we are going to define it algebraically. So you have a collection A of atoms, a countably infinite collection. Everybody understands countability, infinity, and so on and so forth. Yeah. So it's countably infinite. So it is not it's not uncountably infinite, for example, and it's not finite. It's not finite because every time I require a fresh atom, I should be able to get one. Right? Okay, and then I have a collection of operators, omega, uh, and I'm going to represent these propositional logic elements in green. Yeah. So this is the notation I'm going to use for the various operators. The first one is not, the second one is and, the third one is or, the fourth one is a conditional, if then, and the fifth one is a biconditional. Okay. So these are the set of operators and they are disjoint from A. And each operator has a fixed arity alpha, with the negation being a unary operator and all other operators being binary. Right? And of course, in addition to these, of course, we will use various kinds of parentheses as grouping, for grouping. And what we say is that P naught is the smallest set generated from A and omega. Is there anybody who does not understand this last sentence? Yeah, you don't understand that? Okay. So what we'll do is, we'll give an alternative definition in terms of a Backus-Naur form. That's standard practice in programming languages, so we'll follow that, right? So, and then I'll come back to what this means by the smallest set generated from A and omega, right? Okay. So, you're familiar with the Backus-Naur form for defining the syntax of programming languages? No? Okay, it's like this. Listen carefully to what I'm saying. So this one, first thing says that I'm going to use phi and psi as what are known as variables ranging over P naught. Okay? So phi and psi represent typical elements of this language of propositional logic. So it's like, let phi be an element of the language of propositional logic. Let psi be another element of propositional logic. Then, so the phi and the psi occur on the left hand side to essentially specify how I'm going to construct propositions from the basic elements. So A, which I wrote in green on the slide, A is a proposition. I'm sorry. Each member of A is a proposition. Okay? And if you look here, the next clause essentially says, so this A here essentially says that every member of A is a proposition. So that means that we started with a collection A of propositional atoms, and that is itself a subset of the set of propositions, yeah, set of elements of this language. The next clause says that I take any proposition, and so let phi be any proposition, and if I put a negation, then this is also a proposition. Okay? Now, for the binary operators, essentially what I am saying is, if phi and psi are propositions, then this is a proposition. right? So similarly, I can say for or, arrow, and okay. So what are we doing? Starting from the countably infinite set of atoms A, we are constructing compound propositions from the atomic propositions by using these operators, right? And what we are also saying, and this needs to be emphasized, is that besides these, nothing else is a proposition. Right? So what we are saying is that you cannot take any junk elements from outside and combine them with the operators of propositional logic in order to get any proposition. Is it clear? So this is how programming languages are defined. By this is known as the Backus-Naur form. I have actually modified the Backus-Naur form modified for the purpose of just defining the language in a brief, in a concise fashion. Yeah. So what we are saying, so this notion smallest is that supposing you didn't restrict yourself to A, you took some set larger than A and started generating compound propositions, then this word smallest ensures that all propositions which contain all elements outside the operators and outside the set A are all thrown out. Even within the set A and the operators, if you construct something like this, right, this is also thrown out. Okay, this is also not something that can be generated by this BN. Right? So essentially what we are saying is that the language has to be defined in such a way that the compiler can parse, any compiler for this language can parse the language meaningfully. It's like saying that it should be compilable. So this last sentence, nothing else is a proposition, and this phrase, the smallest set generated, all essentially say that it should be compilable and there should be no parsing errors. Yeah? Is that right? Okay. So these are known as sentences. So in fact, propositional logic is also called sentential logic. And the main motivation is that somehow, since we are interested in truth and falsehood, we are interested in statements about which it can be stated whether they are true or they are false. So it does not include statements, even from natural language, which are not of this form. Right? So for example, it does not include statements which are like questions. It does not include statements which are like commands. You know, go and do this homework. I mean, that's a command to which normally you cannot assign a value of true or false. Okay? So it refers to essentially, since logic essentially comes from the linguistic philosophy school, it refers to that subset of natural language consisting of those full sentences for which a truth value may be assigned, for which it is at least theoretically it is possible to say whether they are true or false. Right? Okay. So that is what our syntax is going to do. Are there any questions? Do you have any questions? Okay. So, yeah.
The sentence means the element of the language.
Yeah, a sentence is, let's say, a string of the language. Okay. However, okay, a sentence is a string of the language, but of course, the strings of the language contain, in addition to elements from the set of atoms and the operators, they also contain these parentheses. Okay, so for example, so just as this, I mean, you cannot have sentences like this, for example, yeah, and you cannot have sentences like this, for example, right? I mean, the parentheses have to match and this and that and so on. The usual things that are associated with a formal language. Okay. One of the reasons for using parentheses is to remove ambiguity. Okay. The safest thing to do is to use a fully parenthesized language. And what this BNF is, you're all familiar with BNF, right? It stands for the Backus-Naur form, and it is a standard thing that is used for defining the syntax of all programming languages, right? So this BNF essentially gives a completely parenthesized notation for propositional logic, right? And in general, of course, a completely parenthesized notation is safe. But in general, when we actually write, we would not like to put in so many parentheses. So the normal thing is to define. I'll just proceed ahead. I'll just proceed ahead with the normal thing is to define a precedence of operators. So let's look at precedence. This is true starting from your school mathematics. Yeah. So what we are essentially saying is that this biconditional has the low. So we'll follow the convention that this biconditional has the lowest precedence, followed by the conditional, followed by or, followed by and the negation has the highest. So it is often stated that this has the highest precedence. It is also used. It is also used in the form that this binds tightest. Yeah, most of you who have done a course on programming languages would be familiar with these things, right? Going back to your school mathematics, these precedence rules also apply for arithmetic expressions, in the sense that addition has lower precedence than multiplication, and the negative binds tightest. So you can that is of course the unary negation. There is a subtraction binds like addition, but you have to, and then you use grouping of you use brackets and parentheses only when you want to override the precedence, right? All that is of course purely a matter of dealing with strings, but we don't actually want to look at it this way. We want to look at all these things essentially. So instead of looking at it as strings and breaking your heads about parentheses and so on and so forth, the simplest thing to do is to look upon them as essentially trees. Okay, so you can think of, since all these well-formed, these are what are known as well-formed sentences. So here's the operator precedence convention, which essentially says that negation has the highest precedence, and this should be the, I'm sorry, this is wrong. This should be the biconditional, which I have written here, yeah, has the lowest precedence, yeah. But more importantly, as I said, this kind of thing is dealing with strings and parentheses and so on and so forth, is a completely wasteful activity which can be taken care of by any machine. On the other hand, what we would like to think of these well-formed formulae, these are known as well-formed formulae. These well-formed formulae, we would like to view them as trees, essentially abstract syntax trees. So all of you have studied in programming languages the notion of an abstract syntax tree. So when I construct a well-formed formula, like let's assume that small p is an atomic proposition, small q is an atomic proposition, and R is an atomic proposition. Now, this is essentially a well-formed formula. Actually, this is a completely parenthesized formula, and what this represents is a tree, is an abstract syntax tree, in which I have as a root node the AND operator, and which has two subtrees. The right subtree is essentially just a leaf node consisting of the proposition R. The left subtree is a negation under which there is a subtree whose root is OR and of two atomic propositions P and Q, right? If you view, so essentially we can think of parenthesis as just being used to render linearly these trees. Our meaning are these trees. I mean, what we mean are essentially these abstract syntax trees, but in order to be able to write in a linear form, we use parentheses. And typically, with this precedence convention, we would write this linearly as essentially just this, not P or Q and R. And this, therefore parentheses are not really necessary, except when you want to ensure grouping in a particular order. Yeah. So these two well-formed formulas are going to be considered syntactically equal, because the only difference is in the use of in the removal of redundant parentheses, right, according to the precedence convention. So we will think of these as essentially being syntactically identical. Yeah, and so what we will do now is, so now this is going to be our basic tool set, and whenever I mention a proposition, it's up to syntactic identity. Basically, think of it this way: two propositions written differently are syntactically identical if they have the same abstract syntax tree. Right? Is it fine? So as long as they have the same abstract syntax tree in which no parentheses are used, we consider them to be syntactically identical. Right? Okay, I'll stop here today.